Welcome back to my channel. Today I brought a topic related to the area of parallelograms and a triangle. Okay, we'll see the different, try to prove the different theorems. Okay, here is the first theorem. You can see here, parallelograms standing on the same base and in between same parallels are equal in area. Okay, we need to prove the parallelograms standing on the same base. Okay, for that, we try to draw first a pair of parallel lines. AB is parallel to CD. Now we have to create the two parallelograms on the same base, AB, and in between parallels AB and CD. Okay, for that, we can just draw something like this, the two triangles in this way, so that we can get the two parallelograms on the same base, AB, and in between parallels AB and CD. Now here, what is given? Let's see. Parallelogram ABFC and parallelogram ABDE are standing on the same base AB and in between parallels AB and CD. Now we need to prove that these two parallelograms are equal in area. Okay. Now for that reason, let's see that how can we prove it. Here, you can see in the figure, okay, that's a parallelogram standing on the same base. Now you can see clearly the two different triangles over there, ACE and the BFT. If you're able to prove them congruent, I think that we can prove the parallelograms are equal. Let's see how we can do that. In the first step, see, let's write the facts and reason columns over there. And in the first step, the first number, we can say that in triangle ACE and BDF, let's think how we can make them congruent, okay? There are different axioms to prove them congruent. So let's take the first one as the angle C is equal to angle BFT. So are they equal? Yes, of course, they are equal. Because the reason is corresponding angles, AC is parallel to BF. I think you can clearly see that, right? And here, the next one is in number 2. See what we can say. Angle AEC is equal to angle D. Okay. Now, they are also the corresponding angles. You can just write the corresponding angles. And this time, the parallel lines are A is parallel to BD. Got it? We got angle and angle. Now, let's find out the one side. So we can say that AE is equal to BD, right? AE is equal to BD. It is the opposite sides of the same parallelogram, ABD, right? Opposite sides. So we have got here angle side. So we can say that the triangles ACE is congruent to triangle BDF. And what's the reason? By angle side axiom. Now, once the triangles are congruent, what will happen? Your areas will be equal. We can say triangle AC is equal to triangle BDF, right? We know that area of congruent triangles, they are the areas of the congruent triangles. Okay, now in both equal areas, if we add something equal, then the result will be also equal. So we can add on the both triangle the trapezium ABFE. Okay, in the both sides, both the triangles, we can add this trapezium. And the reason we can write that adding trapezium ABFE on both sides, isn't it? Now the next step, we can say that if you add in triangle AC the trapezium ABFE, look at the figure, what will happen? It will become a parallelogram ABFC, and that is equal to parallelogram ABDE, right? The whole part axiom. So we can write a reason from the fact 3, and that is called the whole part axiom. Okay, this is the first theorem that we prove it. Okay, the next one, hence the theorem is proved here. You can write a conclusion and you can just write a proof here. Okay, let's look at the next theorem. The next theorem is something like this. Look at here. Area of triangle is half of the parallelogram standing on the same base and in between the same parallels. So let's consider this is theorem number 2, right? In order to prove this theorem, we have to take the help from the first theorem. Okay, just consider what we proved in the first theorem. In the first theorem, we proved that parallelograms standing on the same base are equal in between parallels. Okay, now we are going to take that, the first theorem as a reference for in order to prove this theorem. Okay, now first of all, let's draw the figure, and we have here the pair of parallel lines as it is the same way. AB is parallel to CD, and here we can just what we can do, we can create a triangle and a parallelogram. Okay, here you can see the triangle ABC standing on the base AB and in between parallels AB and CD, right? And let's create another parallelogram. That's one is like something like this. You can see the on the base AB that a parallelogram is ABD, right? So let's write the given here. So what is the given? Let's look closely here. You can see parallelograms ABD and triangle ABC are standing on the same base AB and in between parallels AB and CD. Got it? Now we have to prove here. What we have to prove here? It is the triangle ABC is equal to half of the parallelogram ABDE. Okay, now let's prove this one. I already told you that we have to use the first theorem, that which we have proved, in order to prove this theorem. Now, did you remember in the first theorem what we did? We just proved that the two parallelograms standing on the same base and in between parallels are equal in area. But here is the only one parallelogram. So can we create another parallelogram so that we can just use the first theorem here? So what I do is that I will just join BF, not only join, I draw the line BF parallel to the AC. So let me write here in the construction, BF parallel AC is drawn. Because why I'm doing that? Because we did two different parallelograms so that we can use the first theorem in order to prove this theorem, right? Okay, here I did the construction. Now the next facts and columns, regions, let's write it. And in the number one, I can say that ABFC is a parallelogram because I have constructed, right? And I can say ABFC is a parallelogram. Why I can say that? Because the reason is by construction, we have made BF is parallel to AC. And from the given, it is already given that AB is parallel to CF, isn't it? Because AB parallel to CD means AB parallel to CF. So ABFC is a parallelogram, we can say that. Okay. Now in the number two, what we can say? The triangle ABC. Look at the triangle ABC. Is it half of the parallelogram ABFC? Yes, of course. Why not? Because see, BC is a diagonal, and you know that diagonal bisects. That is the fact. Okay. BC is a diagonal, and diagonal bisects the whole parallelogram into two parts. So we can express the triangle ABC in terms of half of the parallelogram ABFC. Okay. Now here, from the first theorem, we already proved that if the parallelogram standing on the same base, they will be equal. So we can say that parallelogram ABFC is equal to parallelogram ABD, right? Because they are standing on the same base and in between parallels. So we can write the reason parallelogram standing on the same base AB and in between parallels AB and CD. Got it? Now, since they are equal, now if we compare, okay, if we compare the fact number 2 and 3, what we can say? Can we say like this? Triangle ABC is half of the parallelogram ABDE, right? Parallelogram, triangle ABC is equal to half of parallelogram ABDE. Now we can say the reason from facts 2 and 3. Here is another theorem. Area of triangles standing on the same base and in between same parallels are equal in area. Okay. Now here we need to prove this one, and here is the figure here. You can see clearly the two triangles standing on the same base AB and between same parallels. Can you figure out which are the triangles here? Let's write it given. Okay. Here you can see the triangle ABC and triangle ABD are standing on the same base AB and in between parallels AB and CD. Now what we need to prove here, it is a triangle ABC is equal to triangle ABD. Now I already told you that in order to prove this theorem, we have to use the theorem number 2, where we have proved that the triangle is equal to the half of the parallelograms. Okay, that's we already proved that. So we are going to use that concept here. Okay, let's look at here. See this figure. In order to prove this one, we need the help of the second theorem, that is the area of the triangle is equal to the half of the parallelogram. But here in this figure, you can see only two triangles. So we need a one parallelogram, right? So in order to do that, can we construct like that? BF is parallel to AC. Now let's write a construction. BF is parallel to AC is drawn because we need a one parallelogram in order to prove this theorem, right? Now here, let's write the facts and reason columns. And here, the first number I can say ABFC is a parallelogram. Can you say me the reason why? It's the same thing. We have constructed the BF is parallel to AC, and in from the given AB is already parallel to CF. Okay, that is AB is parallel to CD. Okay, now we can say here triangle ABC is a half of the parallelogram ABFC. Look at the triangle ABC. It is just half of the parallelogram ABFC. I already mentioned that BC is a diagonal, and you know the diagonal bisects the parallelogram, right, into two equal parts. Now let's write here the triangle ABD. Look at the triangle ABD. It is standing on the base AB, and the parallelogram ABFC is also standing on the same base, right? And in between parallels. So can we say that their ABD is half of the parallelogram ABFC? Yes, of course we can say that. And what's the reason? Parallelogram and the triangle standing on the same base AB and in between same parallels AB and CD, right? Now if you compare the two facts number 2 and 3, see both the triangles are equal to the half of the same parallelogram. So we can say here now ABC is equal to ABD, right? And the reason is from facts 2 and 3. Hence, it is proved